In this video, we'll start our discussion on how to solve homogeneous systems of differential equations. But before we get started, let's recall a key scalar differential equation. So suppose I have the differential equation dy dt equals to lambda y with some initial condition. Then we know that the solution to this is going to be y of t equals to the initial condition e to the lambda t. And you can really think about the scalar differential equation as a 1 times 1 system of differential equations. And so in this video, I will show you how you can use the tools of linear algebra to use this result for the scalar differential equation in solving systems of differential equations. So the plan is we will use linear algebra to use what we know about the scalar system to solve a 2x2 system. Okay, let's consider an example. So suppose I want to solve the system of differential equations du1 dt equals to u2 and du2 dt equals to u1. And suppose I have some initial conditions like this. Okay, so now the idea is that I want to turn the system into two scalar problems. And to do this in this case, I consider w equals to u1 plus u2. And now I want to write a differential equation for w. And so note, if I differentiate both sides, I get dw dt equals to du1 dt plus du2 dt. But now we can go back to our definition for the differential equations, and we know that du1 dt is the same as u2, and du2 dt is the same as u1. So this becomes u2 plus u1. But note that u2 plus u1 is the exact same as w. So in other words, I've written down now a differential equation for w. And note that we can write down an initial condition for w, which is w at 0 has to be the same as u1 at 0 plus u2 at 0, which is u01 plus u02. But this is a scalar equation now, so we know how to solve it. And so we know that w of t must be the initial condition w0 e to the t. Similarly, we can write down a second differential equation. So I can say z equals to u1 minus u2. And then once again, going through the same process, I can write down a differential equation for z. So dz dt is going to be the same as du1 dt minus du2 dt. Once again, we look up what du1 dt is. So du1 dt is the same as u2, and du2 dt is the same as u1. And note that this I can rewrite once more as negative u1 minus u2. So in other words, this becomes negative z here. And similarly for the initial condition for z, so I can say once again that z at 0 has to be the same as u1 at 0 minus u2 at 0. So I get u01 minus u02. So once again, we end up with a scalar differential equation for z, which we know how to solve. So z of t is going to be z at 0 e to the negative t. Okay, having found solutions for w and z, we now want to rewrite these solutions to obtain solutions for u1 and u2. So let's just recall that w is the same as u1 plus u2, and this we found equals to w0 e to the t, and similarly that z equals to u1 minus u2, and that equals to z at 0 to e to the negative t. Okay. Let's call this equation 1 and this equation 2. And now I want to solve these two equations to find an expression for u1 and an expression for u2. So to find the expression for u1, I add equations 1 and 2. So I get that 2u1 equals to w0 e to the t plus z of 0 e to the negative t. And similarly, to find an expression for u2, I say equation 1 minus equation 2. So I get 2u2 equals to w0 e to the t minus z of 0 e to the negative t. So this means that u1 of t is some constant e to the t plus some other constant e to the negative t, and similarly u2 of t is some constant e to the t minus some constant e to the negative t. This is how you would solve a system of differential equations. However, our method here has a big disadvantage. The disadvantage here is that we had to guess these two special combinations of u1 and u2 that transformed our system of differential equations into two scalar equations that we knew how to solve. It turns out that if instead we write this system of differential equations as a matrix equation, then these two special combinations turn out to be the eigenvectors of that matrix. And this is the topic for the next video. See you all there.